y'all, welcome to Miss Clark's chemistry class. This is the first lesson in a series of lessons about nuclear chemistry. This lesson specifically, what is radiation? Did you know that radiation comes from the nucleus of atoms? Well, go get your notes, get your periodic table, and let's get started. So first, let's start out with a very general definition of nuclear chemistry. Now, I'm hoping that you're seeing that word nuclear and it's making you think of nucleus, because that is exactly where this chemistry is taking place, in the nucleus. So a broad definition could be any changes to the nucleus. Any changes in the nucleus, we're going to call that nuclear chemistry. Up until now, when we've talked about the atom, we've not really dealt with the nucleus very often. It's all about the electrons. In fact, it's not even all about the electrons, it's all about the valence electrons. We've been learning in chemistry that the valence electrons basically rule the world. It's the valence electrons that dictates what atoms are going to bond together. It's the valence electrons that bond those elements together. So far, just about everything in chemistry we've talked about has always dealt with electrons. Well, in nuclear chemistry, that is about to change. We're focusing pretty much solely on the nucleus. And I'm going to be honest with you, in this lesson, all of these lessons that we're going to go over nuclear chemistry, we're going to talk about some things that are brand new. And some of these ideas are going to be a little bit out there. But before we go on, let me give you the true definition of nuclear chemistry. A subfield of chemistry dealing with radioactivity, nuclear processes, and changes to the nucleus like transmutation. Changes to the nucleus, that is what nuclear chemistry is all about. Let's talk about this word transmutation, and it's a vocab word. And transmutation just means a change to the nucleus. I'm going to teach you things like protons are actually made up of neutrons and positrons, and that neutrons are made up of protons and electrons. The nucleus has the ability to break its subatomic particles, those protons and neutrons, into smaller particles. I know that's kind of crazy, right? And before we go any farther, let me just tell you what these little nuclear particles are called. You know, we normally say protons and neutrons are in the nucleus. That's still true. Protons and neutrons are in the nucleus. And since nuclear chemistry is dealing with these protons and neutrons, there is a vocab word that just kind of lumps those two terms together, and that's called a nucleon. So a nucleon is just the particles of the nucleus. I'm going to use this word nucleon throughout this whole unit, so I just want to make sure that from the very beginning, we talk about what a nucleon is. And the nucleon, that's just a general phrase for all the particles in the nucleus, especially the protons and the neutrons. So let's talk about nuclear reactions, but more specifically, I want to contrast nuclear reactions and chemical reactions, because we've already been learning about chemical reactions. So in chemical reactions, that's where we rearrange elements and get new compounds. Well, when we get new compounds, those compounds are held together by a chemical bond. So chemical reactions are about breaking and rebuilding chemical bonds. And when we talk about breaking and rebuilding chemical bonds, those chemical bonds always deal with those valence electrons. Every chemical bond deals with valence electrons. And the way just about every chemical bond works, no matter if it's ionic bond, covalent bond, those chemical bonds always hold atoms together based on opposite charges attract. The positive nucleus is attracted to the negative electrons, and that positive and negative attraction glues the atoms together. We call that force of attraction between pluses and minuses, positives and negatives, electrostatic force. We've also learned that there's energy stored in these bonds. Now let's flip and talk about nuclear reactions. Nuclear reactions have nothing to do with electrons. They don't have anything to do with that force of attraction between positives and negatives. Nuclear reactions are occurring in the nucleus. In the nucleus, there is this thing called the strong force. This strong force, it holds all the nucleons together. Let me write that down. We just remembered how positives and negatives attract each other, and remember the opposite of that. Two positives are going to repel each other. Two negatives are going to repel each other. Like charges repel each other. Let's go back to the nucleus again. There are positive protons and there are neutral neutrons. To have an overall charge of a nucleus, to be positive. So if we kind of put that together with the thought of like charges repelling, it would seem like the nucleus would be impossible to hold together because it is nothing but positive charges. Of course, the neutrons, they're neutral, so I'm not going to count those. There's got to be this energy in the nucleus that kind of corrals these protons and neutrons so they can be glued together. And we call this the strong force. Now, this strong force is exactly what it says it is. It is a very, very, very strong force. Much, 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 much stronger than the electrostatic force that holds atoms together to form compounds. We're talking about a force that holds positive charges together. Just as a chemical reaction is the breaking and rebuilding of these chemical bonds, a nuclear reaction is the breaking and rebuilding of the strong force. When you have enough energy to break the strong force, that is a huge amount of energy. So whereas we said chemical reactions have energy stored in their bonds, that energy does not compare at all to the amount of energy that's stored in nuclear reactions. So I'm going to put a great deal of energy. That energy is released when we start messing with these strong forces. And I don't mean we like we're doing something. I guess just like we in nature. When a nuclear reaction occurs, it emits radiation. Oftentimes, particles and energy get thrown out of the nucleus as a byproduct. This stuff that gets thrown out of the nucleus, these particles, this is called radiation. Okay, so let's just say the radiation is the particles that are kicked out of the nucleus as a result of a nuclear reaction. But before we leave radiation, there's two types, ionizing and non-ionizing. Ionizing, that's the worst. This is the most dangerous. And the reason why ionizing is so dangerous is because ionizing radiation is radiation that can kick electrons out of atoms, forming ions. So ionizing radiation, it's very dangerous. It's dangerous because this type of radiation can remove electrons from atoms to form ions. That means we're changing molecules. Ionizing radiation can change your molecules. When you think about radiation causing cancer, that's ionizing radiation. Non-ionizing radiation has only the ability to move electrons within their energy levels. So if an atom gets hit with non-ionizing radiation, it excites those electrons. The electrons jump up energy levels, then they fall back down and they emit energy. Oftentimes they emit visible light. They can also emit infrared. They can emit low doses of UV. And before we move on, remember the electromagnetic spectrum where we have, now see, I always have to use my mnemonic device, raging Martians invade Venus using X-ray guns. So that's radio waves, microwaves, infrared, visible light, UV, X-ray, and gamma. We do consider all of these types of waves to be radiation. And if you can also remember far enough back, that this end is where the low energy waves are, and this end is where the very high energy waves are. And the line between ionizing radiation and non-ionizing radiation, right here at UV. And that's just because of this lower energy. There's not enough energy in these waves to remove electrons. There's only enough energy in these waves to excite electrons. And then again, we go back to UV. The higher energy side of UV plus X-ray and gamma, very, very, very high energy. In fact, their energy is so high, they can kick out electrons. And when you can kick out electrons and make ions, that's called ionizing radiation. Okay, so we've talked about what a nuclear reaction is. We've talked about radiation. Let's talk about radioactivity. I've mentioned that these nuclei are going to go through some change. I've also mentioned that the nucleus is going to kick things out. Well, while the nucleus is doing these things, that's called radioactivity. Now let's talk a minute about why the nucleus is doing these things. When a nucleus is too large, or the ratio of protons to neutrons in the nucleus is like out of whack, It causes the nucleus to become very unstable, kind of like an excited electron. An excited electron that's jumped out to the highest energy levels, very unstable, quickly falls back down. A nucleus that is too large, or a nucleus that has a disproportionate number of protons and neutrons, also becomes very unstable. And this is what is at the basis of nuclear chemistry. When a nucleus becomes unstable, it'll make changes to itself. It can change a proton to a neutron. It can change a neutron to a proton. And when the nucleus makes these changes, like changes protons into neutrons, neutrons into protons, we call this decay. The nucleus is decaying. And so radioactivity is just the spontaneous decay of a nucleus. A lot of these words really go hand in hand, and it's kind of hard to keep them super separated. Radioactive decay just means the emission of particles from an unstable nucleus. Now, if we go back, these particles that are emitting from the nucleus, that's called radiation. The process of emitting these particles from the nucleus, that's called radioactive decay. The particles themselves that are coming from the nucleus, this is radiation. And the whole thing, that's radioactivity. We call the nucleus that's undergoing the decay a radioactive isotope. Because if a nucleus is unstable and it's having nuclear reactions, having nuclear decay, that's radioactive. Because the stuff it's spitting out, those particles, that's radiation. So a more specific name for the unstable nucleus that's undergoing decay is a radioisotope. Okay, so I just put that a radioactive isotope is an unstable nucleus that's radioactive. Now, I didn't list radioactive as one of my vocab words. If you have a nucleus that's big and unstable, it's radioactive. Now, I did mention that word isotope. Did I blast you from the past just a tiny bit? Let's remember what an isotope is. It's been a while. Okay, so remember that an isotope, same element, but they have a different mass number. So I'm just going to write same elements, different mass. And I'm pretty sure the example that I used when I talked about isotope a long time ago was carbon. Carbon, that's number 6 on the periodic table. And if you look at the periodic table, its mass number is 12. But there are such things as carbon 13 and carbon 14. When we're naming an isotope, we always use its name and its mass number. I couldn't use the atomic number to identify the difference between these 3 types of carbon, so it would have to be the mass number. So we would call this carbon 12, carbon 13, carbon 14. They're isotopes of each other. They all have the same number of protons. They each have 6 protons, but since their mass numbers are different, they have different numbers of neutrons. Now remember, mass number is the protons plus the neutrons. If I want to get the neutrons, I need to subtract. 12 minus 6 is 6. The number of neutrons here would be 7, and the number of neutrons here would be 8. So isotopes, same elements of each other, different mass numbers because they have different number of neutrons. When we were talking about isotopes, we also learned how to write the information in shorthand, which I have been doing. I have been using isotopic notation, even though I wasn't even quite ready to do that yet. When you're talking about isotopic notation, or some people just call it isotope notation, okay, so you're going to have this element, you're going to use the chemical symbol, and then you're going to have this top number, we call that A, that stands for mass number. And then we're going to have Z, that stands for atomic number. And we've already got some examples. Carbon, atomic number was 6, its mass number is 12. This carbon, atomic number 6, mass number 13. Carbon, atomic number 6, means it has 6 protons, mass number 14. So isotopic notation, you're going to write the symbol, mass number, atomic number. Mass number is always going to be on top. The big number is always going to be on top. We talked about the things that the nucleus spit out. Let's talk about a few of those. The first one we're going to talk about is an alpha particle. Sometimes the nucleus is so big that it spits out an alpha particle. Now, an alpha particle is made of 2 protons and 2 neutrons. You may have heard of alpha particle before, especially if you've already talked about the history of the atom and you talked about how Rutherford shot alpha particles at gold foil, and that's how he discovered the nucleus. Alpha particles, same thing. Now, if you look at the periodic table to see what element has 2 protons, that's helium. And if you look at helium on the periodic table, it has a mass of 4. Well, if you add up the 2 protons and the 2 neutrons, you get 4. So basically, an alpha particle is just a helium nucleus. I know 2 protons and 2 neutrons, that doesn't seem very big, but in the nuclear world, that's pretty big. So we consider the alpha particle to be large and slow moving. Since it's large and slow moving, it has a low penetration power. Penetration, the things that it can go through. And if it can go through something, then once it gets to the other side, it can wreak havoc. So if it can't get through, it's not so dangerous. If it can get through, it becomes more and more dangerous. The less penetrating power radiation has, the less dangerous it is. The more penetrating power radiation has, the more dangerous it is. Alpha is an ionizing type of radiation because we're kicking things out of the nucleus. We're making changes to that atom. And so it is ionizing, but it's not quite as dangerous. In fact, you can find alpha particles in most smoke detectors. Now let's talk about the things that'll stop an alpha particle. It's low penetrating. It can be stopped by things as thin as your outer layers of skin, paper. So you can see alpha particles not very penetrating. Now the second type of particle that a nucleus may decay into and spit out is a beta particle. A beta particle is a high energy electron. So sometimes the nucleus can spit out high energy electrons. Did you even know a nucleus could contain an electron? That's a brand new idea. I'm going to come back to that in a separate lesson specifically on beta particles, so make sure you come back and listen to that. Now, it's a high energy electron. We know electrons are teeny, teeny, tiny. And since it's so tiny, it's also very fast. And if it's very small and very fast, it has a higher penetrating power. So it is more penetrating than alpha, meaning it is more dangerous than alpha. It can be stopped by aluminum foil, clothing. A beta particle is more dangerous than an alpha particle. Also, still considered to be ionizing. And then the third type of the most common radiation that a nucleus will emit while it's going through nuclear decay is gamma. Now, I talked about gamma a second ago. Remember, that was on the electromagnetic spectrum. If it's on the electromagnetic spectrum and it's part of the light given off from the sun, it can't be a particle. It's just energy. We call this a gamma ray instead of particle. Very high energy. It has the highest energy out of all three. It has such high energy, it has molecule changing potential. Now, alpha particles and beta particles, they do have the ability to change molecules. The thing is they're not getting down into the body. They're being stopped before they can get that far. Gamma, not much can stop it because it is the most penetrating out of the three. Between alpha, beta, and gamma, gamma is the most penetrating. The things that can stop gamma are inches of lead or feet of concrete. That's right, inches of lead, feet of concrete. Now, I realize X-rays and gamma rays are not the same thing, even though they're right beside each other on the electromagnetic spectrum. X-rays, also pretty dangerous. They're ionizing radiation, actually. They're not as high energy as gamma, or we wouldn't use X-rays for the tools that we use X-rays for. You know, when I think of an X-ray, I kind of think of a good thing. When I dislocated a bone in my foot, thank goodness we had X-rays to tell us if that's what was going on. Do you ever notice when they put that lead vest on you, especially at the dentist? We get X-rays at the dentist, once a year? And they put that big vest over you. It's actually my favorite part of the dentist. I love that thing. It just makes me want to hibernate and go to sleep. The reason why you're being covered by a lead apron, that's right, is to block the radiation from your vital organs. If you've ever seen an image of a nuclear power plant, it is tons and tons of concrete. Concrete, lots of concrete. That's the reason why it takes feet of concrete to block gamma radiation. Let's talk about ways we can detect radiation. If radiation's dangerous, then we need to know when it's around. There is this machine called a Geiger counter, and if you've watched any TV where there's any kind of nuclear situation or radiation, you've seen a Geiger counter. It's that little box thing, and it looks like it has a little microphone that comes off of it, and it makes this like clicking weird sound. That's a Geiger counter. And so a Geiger counter detects radiation. There's also something called a film badge. If we go back and think about that dental hygienist that took our X-rays, I wonder how many X-rays this person takes a day, a week, a month. X-rays are dangerous. They're ionizing radiation. Oftentimes, they'll have either on their name badge or they'll have somewhere else as a badge, and it'll have a little piece of film on it. This film tells them how much radiation they have come in contact with to make sure that they're not being overexposed. Look for that the next time you're getting an X-ray. Now, I keep talking about radiation like it is just the worst thing ever, but actually there's a lot of good uses for radiation. It produces a lot of energy. which I will talk more about in a future lesson. It's also all over medicine. Think about cancer treatments. You get radiation to help with cancer, but not only cancer treatments, radiation's also used in a lot of diagnostician tools like the PET scan, radio tracers, radioisotope tracers. There is quite a bit more that radiation does in medicine, but let's move on, right? Sterilization, goggle cabinets. I know in my classroom, I have a goggle cabinet and it's a UV goggle cabinet. You can put your goggles in there, turn the timer on, blast it with UV, kills everything. There's also gamma sterilization. You use an isotope of cobalt and it emits gamma and it will kill every germ on the instrument. And then archaeology. Archaeology uses radioactive isotopes to date bones. Have you ever heard of carbon dating? Carbon dating is using radioactive carbon isotopes to see how old bones are. Let's talk about where radiation comes from. You would actually be surprised to learn that a lot of radiation actually just comes from the earth, from nature, in the soil. The minerals and all the different elements that are found in the earth are going to have a variety of different isotopes. And some of those isotopes might be unstable. And if they're unstable, again, due to very large nucleus or a disproportionate between protons and neutrons, they're going to go through spontaneous decay. The thing is most of the time that source of element that's there that's decaying isn't big enough to really cause us much trouble. Radiation does occur naturally in nature. Also, we just talked about a lot of medical uses. Well, if medicine is using radiation, then they're also going to be the source of some of that radiation that's out in the atmosphere. A nuclear fallout. This is like what happened at Chernobyl when their nuclear reactor had a big meltdown and just leaked radiation out into the environment for a very long time. And then there are several other that I'm not going to get into. Now, problems with radiation. Because we've talked about radiation being bad. We've even talked about radiation being good. So if it's good, what's the problem with it? Disposing of the waste can be expensive. It can be costly to the environment. So that's a huge problem. Also, we talked about that meltdown a while ago. These reactions are crazy hard to control. If any mistake occurs, then you can have a nuclear meltdown, and that is a huge problem. Radiation causes chromosomal damage. We know we can use radiation as a medicine for cancer, but radiation also causes cancer. Think about being out in the sun too long, all those UV lights. That's why you have that lead vest when you're getting an x-ray, is so you don't expose your body to too much radiation, because exposing your body to too much radiation causes chromosomal damage. It also can cause organ damage with all that ionizing radiation. The most sensitive areas to your body to radiation, to this chromosomal damage, destroys organs or forms tumors, is going to be the cells in your body that reproduce the fastest. Skin cells replicate fast. Cells in your thyroid replicate really fast. Red blood cells, your eye cells, liver, all of these types of cells that reproduce quickly, if they get too much radiation, it kind of messes up their ability to reproduce correctly, and they go crazy and reproduce like crazy, and then that's how you get a tumor. So we do not want chromosomal damage or organ damage, and that is a problem with radiation. Who knew energy that came from such tiny subatomic particles could be so massive and could also be so dangerous? We've learned about the different kinds of decay, alpha decay, beta decay, but we have got to know how to write those equations out. And that lesson's coming next, so make sure you stay tuned. Until next time, bye y'all.